Okay. Jonathan, I think we can start real life.
Perfect. Good morning, everyone. I can see people are still joining, so we'll give it another minute or two before we get started. Okay, I think we're good to begin. Welcome everyone, and thank you for joining us this morning. My name is Jonathan from Cadence Design Systems, and I'll be supporting today's session, helping with timings and monitoring questions as we go. If you have any questions during the session, please feel free to put them in the questions box, which you'll find in the top right-hand corner of your screen. We'll address those in the Q&A session at the end in roughly 30 to 40 minutes time. Today's webinar will be presented by Marcus Eckert, Managing Director of UNIKE Design and Development GmbH. Marcus is a mechanical engineer and simulation expert with over 20 years experience leading UNIKE, a long-standing MSc software partner supporting industrial customers in simulation-driven product development. His work focuses on developing efficient simulation workflows, delivering validated results, and applying practical engineering methods that help reduce development risks and improve product performance. Marcus is also currently completing his PhD on fatigue simulation of short fiber reinforced plastics under random excitation, and is also a certified international welding engineer. With that, I'll hand over to you, Marcus.
Thank you for the introduction, Jonathan. Without any further ado, I would start the webinar here. So welcome to the webinar. Today we are looking at a topic that may sound very specialized at first, but is typical for many simulation-driven engineering workflows. We do not only want to simulate a component, we want to design a real tool that can later be manufactured and operated reliably. The specific case is a contour near induction coil for selective surface hardening. The coil has to heat only clearly defined surface regions. At the same time, it has to be manufacturable as an internally cooled pressure-tight copper component using additive manufacturing. The central question is therefore, how do we move from the required hardening zone through electromagnetic thermal simulation and optimization to a printable functional inductor geometry? I will walk through this digital chain today using Mark Mentat, Odyssey, and CMFACT Additive. The next roughly 35 minutes of presentations are structured into 5 blocks. First, we look at the technical problems. Why is a contour near induction coil needed at all, and why is the design not trivial? We then move into the physics, alternating current, magnetic fields, eddy currents, Joule heat, transient temperature response, and phase transformation. In the third step, we translate these simulations results into optimization responses and show how Odyssey can make expensive CAE runs usable in an efficient exploration workflow. After that, we look at the additive manufacturing side. The optimized geometry must be printable without losing its function through distortion, leakage, or insufficient surface geometry. Finally, we close the loop with validation, leak tests, cycle tests, and metallographic evidence. The order is intentional because it follows the engineering path from requirement to the real tool. The project context can be summarized quite well as coil 4.0. Traditionally, induction coils are developed with a strong reliance on experience, prototypes, and manual correction loops. That approach can work, but it becomes expensive and increasingly difficult when the hardening zone is geometrically complex. The goal is therefore a more simulation-driven process. We first define the required local heating and then derive the coil geometry from that requirement. At the same time, the boundary conditions of the tool must be respected. We are dealing with a copper alloy with high electrical and thermal conductivity, thin walls, internal cooling, leak tightness under pressure, and a part size that remains manageable for additive process. These values should be understood as a target envelope for this development approach, not as a universal data sheet promise. The red thread is the digital chain from hardening target to thermal model to geometry optimization to additive manufacturing, build simulation, and test. Why is the simulation and optimization effort worthwhile? Induction heating is attractive because the heat generated directly inside the workpiece. By adjusting current, frequency, distance, and coil geometry, we influence intensity, penetration depth, and the time-dependent temperature response. For simply rotational symmetric geometries, engineering experience can take us quite far. For gears and cams, complex surfaces, or local hardening zone, it becomes much more difficult. The electromagnetic field is not directly visible, and small changes in air gap or coil contour can have a strong effect on the heating pattern. The classical loop of building a coil, testing it, reworking it, and testing again is therefore slow and expensive. Simulation changes the economics of process because it makes field distribution, thermal history, and the resulting phase responsive visible before hardware is manufactured. The slide shows the actual engineering challenge. We have the workpiece, the surrounding air domain, and the copper inductor. The goal in the workpiece is not simply as hot as possible. We need a targeted temperature time history in specific surface zones. These zones should reach the transformation temperature, while the core and neighboring features should not be exposed to unnecessary thermal load. At the same time, the inductor itself is a tool with its own requirements. It must generate the desired field, must not overheat, must be internally cooled, and must remain leak-tight under pressure. The third level is additive manufacturing. The optimized geometry must not be changed by distortion, rough channels, porosity, or leakage to such an extent that the electromagnetic function is lost. This is why the task is not an isolated CAD problem. It's a coupled CAE manufacturing problem. Here, we see the physical starting point, a conventional induction heating setup. While the video is running, it is useful to watch two things. First, the coil geometry and the distance to the workpiece control where the field is concentrated and where the heat is generated. Second, the physical test, the thermal response becomes visible only after the coil has already been manufactured and assembled. For a simple coil, that may be acceptable. For complex contour-near geometries, it quickly becomes a bottleneck. The CAE question is therefore, can we predict the field and the temperature evolution before building the coin, and can we use that prediction directly for geometry optimization? The manufacturing question immediately follows. Can this optimized coil then be printed, cooled, and kept leak tight under cyclic loading? This slide makes clear why the task has to be formulated as an optimization problem. We have design variables such as coil path and offset, the cross-section, current, frequency, heating time, cooling channel routing, and later also build orientation. We have responses such as target temperature, phase fractions, hardening depth, self-heating of the coil, and distortion. And we have hard constraints such as minimum wall thicknesses, lead tightness, surface quality, porosity, build volume, and assembly limits. One important point is that the strongest magnetic field is rarely the best design. A very aggressive field can overheat edges, overload coil thermally, or force a geometry that cannot be printed or sealed. The goal is therefore a robust functional optimum inside the constrained design space. This workflow begins with the target surfaces. Which region should be hardened and how much thermal spreading is still acceptable? From there, an electromagnetic thermal mechanical model is built in MarkManTat. The model delivers response quantities that RDC can use for design of experiments, surrogate models, sensitivities, and optimization. The result at this stage is still only a nominal optimum. Therefore, the geometry is transferred into the additive manufacturing process in CMOFACT additive. Build orientation, support structures, residual stresses, distortion, and the compensation are evaluated. At the end of the chain, we have a printed coil, leak testing, thermal measurements, hardening patterns, and metallographic sections. The feedback is essential. Measurement data and additive manufacturing process results are not filed away. They flow back into material data, boundary conditions, and optimization limits. The physics behind the process can be read as a chain of cause and effect. An alternating current in the inductor creates a magnetic field. The field induces eddy currents in the workpiece, and these currents generate Joule heat. The result is a transient temperature field, which then triggers phase transformation, for example, austenitization during heating and martensite formation during quenching. Temperature gradients, transformation strains, and boundary conditions then lead to residual stresses and potential deformation. For optimization, it is important that we do not look at only one step of this chain. If, for example, we optimize the only maximum temperature, we may end up with a wrong optimum because dwell time, hardening depth, coil temperature, and distortions are not right. We therefore need robust and comparable response quantities along the full chain. To represent this chain in MarkManTat, we model with several domains. The model is with several domains is built. We consider the workpiece, the contour near copper inductor, and the surrounding air region. The air domain matters because the electromagnetic field does not exist only inside the solid bodies. Internal cooling is represented through suitable thermal or fluid-related boundary conditions. The electromagnetic calculation provides the spatial power distribution. In other words, where heat is introduced. This is followed by the transient thermal calculation and, where needed, by thermomechanical assessment. A critical point is material data. Electrical conductivity, magnetic property, thermal conductivity, and heat capacity are temperature dependent. For the steel, phase transformation data must be also included. Without sufficient data quality, even the best looking geometry optimization can move into the wrong direction. On this slide, we see typical results from the field and temperature calculation. The electromagnetic analysis shows where current density and power distributions occur. This power distribution becomes the thermal load and creates the local temperature response in the workpiece. For optimization, this means that we are not optimizing the magnetic field image for its own sake. We use current density and Joule heat to evaluate downstreaming responses, peak temperature, time above a threshold, temperature gradients, phase fractions, hardening depth, and self-heating of the coil. Errors can occur in both directions. Too little localization misses the target hardening zone. Too much localization can overheat edges, thermally overload the coil, or favor geometries that cannot be manufactured. Simulations provide the visibility needed to make these trade-offs specific. The time history is at least as important as the spatial hotspot. For surface hardening, it is not enough to know that a high temperature was reached at some point. Dwell time, heating rate, heat conduction into neighboring areas, and cooling rate are also decisive. These quantities determine which phases actually form and how deep the hardening layer becomes. In parallel, we must monitor the coil itself. How much does the copper inductor heat up? Is the cooling sufficient? What does the load look like over repeated cycles? The transient curves are therefore a robustness indicator. They show whether an apparently good snapshot also works as a process window. In coupled simulations, there is always a compromise between physical detail, numerically stability, and automation. A separated electromagnetic thermal coupling can often be more robust because geometry meshed and time steps remain easier to control. For optimization, however, there is an additional requirement. Every variant must be evaluated consistently and repeatedly. If an automated optimizer compares hundreds of design points, the responses must be extracted at the same locations with the same logic and with stable numerics. Otherwise, we may optimize post-processing artifacts instead of physics. The coupling strategy is therefore not only a modeling decision, it is also part of the optimization architecture. In hardening, temperature is only the path to the real target quantity, the material state. From the temperature time history, we must derive where austenite forms, how martensite develops during quenching, and which hardening zones results. Transformation models can be used for this, calibrated, for example, from time temperature transformation or continuous cooling transformation data. In the implementation, subroutines and material models can be applied, for example, for diffusive transformation based on JMAC formulations and for martensite formation according to Coistin and Marburger. The details are interesting for CAE specialists, but the key point is simpler. Only when we translate temperature into phase fractions and hardening depth, we are evaluating the quality of surface hardening, not just a thermal picture. The slide is intended as visualization of the transient chain. In a heating video, we can see how local the energy input is at the beginning and how the heat then spread through the workpiece. The dynamic behavior matters because the target zone is not just a position. It requires a certain thermal history. The cooling or quenching video, we then see the process does not end with the maximum temperature is reached. The cooling rate contributes to the microstructural fractions form and whether the hardened zone develops as desired. For assessment, this means that we have to look at the entire heating and quenching sequence. An isolated temperature state can look convincing and still fail to produce the correct process response. In the next step, we no longer look only at temperature, but at the material and stress rates that results from it. The austenite animation shows where the heating is sufficient to initiate the relevant transformation. The Martensite plot after cooling then shows where hardened regions can be actually be expected. In addition, the residual stress or dilatation animation makes clear that heat treatment is always also a structural process. Temperature gradients, phase transformations, and mechanical constraints generate strains, stresses, and potentially distortion. For coil design, this means that thermal target fulfillment is only part of the story. A valid process design also has to understand and assesses the mechanical side effects. Here, we built a bridge from simulation to evidence. The slide compares simulated phase responses to metallographic reference information. The decisive question is whether the calculated transformation occurs spatially, where the real part shows the hardening zone or microstructural change. This is especially important for the credibility of the simulation. A temperature plot alone may look plausible, but it does not prove that the desired metallurgical effect has been achieved. What matters to the user is the selective hardening result. The right zone, the right depth, and as little thermal influence as possible outside the targeted area. Validation must therefore include the hardening contour and the microstructural response, not only the temperature field. This slide is a reminder that the thermal process design touches structural mechanics. During induction hardening, local temperature gradients, phase transformations, and boundary conditions create residual stress. Depending on the component and process strategy, these may lead to the formation of unwanted stress states. For the workpiece assessment, this is obviously relevant. For the induction coil, it is indirectly important as well, because the coil distance, position, and repeatability of heating depend on geometry. A process may therefore look thermally correct and still be quality critical if the mechanical response is not controlled. That is why stresses and deformations belong in the assessment of process quality. For Odyssey, to optimize meaningfully, the technical target must be translated into computable quantities. The target response can be, for example, temperature in the hardening zone, phase fraction, hardening depth, or an acceptable thermal spread. Design variables include coil path, cross-section, gap, current, frequency, and heating time. Constraints protect reality. Minimum wall thicknesses, cooling channel sizes, leak tightness, and later also additive manufacturing distortion. One possible objective function can minimize the temperature error in the target zone while penalizing thermal spread outside the target zone, self-heating of the coil, and violations of manufacturing limits. Robustness is also important. A good candidate should not work only for an ideal material data set and a perfect air gap. It should remain acceptable under realistic scatter. The practical value of Odyssey is that not only every insight has to come from a new full simulation. First, representative geometry and process variants are generated using a design of experiments. These variants are computed with high-fidelity marked models. From the results, Odyssey learns surrogate or reduced order models for the relevant response quantities and metrics. This allows us to analyze sensitivities. Which parameters drives the target temperature? Which one influences coil self-heating? And which boundary conditions are critical? The optimization can then search the design space much faster. The final candidate, however, is validated again with the full CAE model. That is essential. The surrogate accelerates the search, but it does not replace the final physical confirmation. Here, we see the difference between a starting geometry and an optimized continuous inductor geometry. The important part is the interpretation. The shape is not arbitrary and is not merely aesthetic CAD results. It emerges from the requirement to guide the electromagnetic field so that the desired surface regions receive the right energy. Local changes in path, cross-sections, or distance change the field concentration and therefore the temperature response. At the same time, the geometry must remain inside the manufacturing window. We are looking at a typical result of a simulation-driven development. Geometry is the adjustable lever, but the optimized target is the process response in the workpiece and the functionality of the tool. This slide is the reality check. In theory, one could optimize a geometry completely freely. In practice, that is neither numerically nor manufacturing-wise sensible. Therefore, the design space is described through parameterized degrees of freedom, mesh morphing, and clearly defined limits. These limits are not secondary details. Minimum wall thicknesses, link tightness, cooling channel cross-sections, powder removal, support structures, and assembly surfaces change what remains of the mathematical optimum. The supply geometry and water routing also have to be adapted so that the flow and electromagnetic function work together. This is not a step backward from optimization. It is a necessary step. Only when manufacturing restrictions are included from the beginning does the optimization produce a candidate that can later work as a tool. The two illustrations on this slide should not be understood as two isolated examples. The key message is that optimization does not stop at coil geometry. Current, frequency, and heating time are independent degrees of freedom and define the optimum together with the local contour. We cannot define one current level and one frequency and assume that these parameters are simultaneously optimal for all hardening zones. Different locations may require different local geometries in order to heat exactly the intended regions. In addition, current and frequency change intensity, penetration depth, magnetic force effects, and thermal selectivity. In principle, even targeted zones therefore needs its own process window, local coil geometry plus a suitable operating point. This is the coupling that the optimization has to represent. Why is additive manufacturing so important in this case? The optimized coil is often easier to design conceptually than to manufacture conventionally. Continuous path and variable cross-sections can follow complex workpiece surfaces much better than classical machining or bending processes. In addition, the cooling can be developed together with the electromagnetic geometry. This matters because cooling cannot simply be added later. It affects wall thicknesses, leak tightness, coil temperature, and available space. Additive manufacturing also enables functional integration such as connectors, flow features, or support-aware geometry details. In this sense, additive manufacturing is not only a manufacturing method, it becomes a design enabler for the entire tool concept. This table shows which additive manufacturing aspects have to enter the CAE loop directly. Wall thickness is not a geometric detail. It determines cooling medium pressure capability and leak tightness. Electrical conductivity depends on the copper alloy, porosity, and heat treatment, and it in return influences the electromagnetic response. Surface roughness affects pressure losses and local hotspots inside channels. Distortion can change the coil gap and with it the field. Support structures influence removal, powder evacuation, and local defects. One project learning was that very thin walls can show leakage risk in certain orientations with laser vector conditions. Therefore, the optimization must not only find the shape, it must also account for the manufacturing and process strategy. With simul-fact additive, the manufacturing process itself becomes part of the validation. The electromagnetically optimized geometry has to become a real copper component. During printing, however, thermal cycles, residual stresses, and distortion are generated. Support structures, build orientation, and subsequent heat treatment influence the shape, the final shape. If the coil gap or the coil channel geometry changes as a result, the electromagnetic optimum can be lost in the real part. In the virtual build process, we therefore assess how the geometry behaves during and after printing. The decisive output is not only a colored distortion plot, but also the ability to compensate the input geometry deliberately so that the printed coil lands closer to the required target contour. Here, we see the distortion assessment before geometry compensation. The distortion on the left side and on the right side views are not additional design variants. It shows the deviation of the printed or virtually printed geometry from the nominal CAD geometry. The colored result represents additive manufacturing induced displacement. The gray reference shows the CAE target geometry. The state shown is important as well. The part is still close to the process condition and influenced by support and build constraints. It is not simply a free-floating ideal best fit compensation. This reveals how the printing process actually shifts the geometry. For the induction coil, this is critical because coil offset, wall thicknesses, and cooling channels are highly sensitive to geometric deviations. The electromagnetic optimum must finally be realized as an actual geometry. This slide shows the actual compensation idea. First, the simulated printed geometry is overlaid with the nominal CAD geometry. In the initial view on the left, the local positive and negative surface deviations become clearly visible. The next step is not to change the target, but to change the input geometry. The CAD is predeformed in such a way that the predicted printing distortion moves the final as-built geometry closer to the desired target contour. The compensation view shows that after compensation, the deviation is pulled back much closer into the tolerance band. For the induction coil, this is central. We do not simply print a nominal optimal geometry, we print the compensated input geometry so that after residual stress, distortion, and post-processing, the functional relevant contour is correct. At the end, the digital workflow has to be closed on the real component. The printed coils provide several levels of validation. First, we assess geometry, surface, density, and conductivity of the copper part. Second, we test cooling and leak tightness. In other words, whether the inductor can be reliably supplied and with cooling medium during operation. Third, we compare actual hardening results, thermal observations, hardening contour, edge sections, and metallographic cross sections. Simulation does not make these tests obsolete. It makes them much more targeted because we know in advance which quantities are critical and which deviations would matter. The measurement data calibrate material assumptions, boundary conditions, and optimization limits. The result is not a linear process, but a closed learning loop of simulation, manufacturing, and validation. This slide is perhaps the most useful checklist. Field gradients require local mesh refinement, control the air gap, and material sensitivities. Coupling instabilities have to be managed with time step control, consistent response extraction, and fallback validation. Material uncertainty concerns conductivity, permeability, and phase data. Additive manufacturing distortion requires build simulation, support strategy, and a compensation loop. Leak tightness requires minimum walls, scan strategy, as well as pressure and flow tests. Finally, the optimizer must not overfit. A candidate that looks optimal in a surrogate model still has to be confirmed with full physics and physical tests. The method is powerful, but it remains engineering. Risks have to be made explicitly and controlled. 4 CAE principles can be derived from the case study. First, we do not optimize geometry for its own sake. We optimize the process response, field, temperature history, phase fractions, and hardening counter. Second, manufacturing is part of the objective. Wall thickness, leak tightness, supports, and distortion must not appear only at the end. Third, data-driven exploration scales the workflow. Odyssey helps to derive sensitivities, robust candidates, and faster spaces from expensive full simulations. Fourth, validation closes the digital loop. Thermal measurements, metallurgical evidence, and additive manufacturing process data turn a plausible simulation into a robust tool concept. In this way, simulation-driven design connects the desired hardening pattern with an inductor coil that is actually printable and pressure tight. How would we start a similar project? First, the hardening target must be described precisely. Which surface zones, what acceptable thermal spread, and what time-dependent process. Next, a baseline model is built, including geometry, material data, cooling, and electromagnetic setup. In the third step, metrics are extracted: temperature, phase fractions, coil temperature, and manufacturing constraints. Only then the systematic exploration with design of experiments, surrogate models, sensitivities, and robust candidates become useful. In parallel or directly afterwards, the additive manufacturing build has to be validated, including process simulation compensation and a physical test plan, of course. 4 takeaways should remain. Target hardening needs response-driven design. Mark method makes the physics measurable. Odyssey accelerates the search. Seam effect additive protects manufacturability. This brings me to the end of the presentation. Thank you for your attention, and I'm looking forward to your discussions and questions.
Brilliant. Thank you, Marcus. So that brings us to the Q&A part of the session. We have some questions in the chat, so we'll start with those. Just as a reminder, if you do have any questions, please do pop them into the question box on the right-hand side, and we'll get through as many as we can. So we have a couple who have come in. So question 1, Marcus, what is the minimum material data you need for multi-physics, especially for heat treatment?
Yes, it's crucial. So it starts with the material data, of course. Otherwise, you're not able to predict the hardening depth, for example. Therefore, a really crucial parts are the TTT or the phase transformation diagrams. Besides that, you get easy hands on the permeability for the magnetic behavior. That's something that is freely accessible on the internet, but TTT is something that is mandatory, as well as the powder, the copper alloy for the manufacturing for the printing process.
Brilliant, thank you. And one more question. How can you define the meaningful response quantities?
Oh yeah, that's a good question. So as I laid out, one of the hardest task for the customer itself is to articulate the right question. So what kind of areas I'm really targeted on? What is my goal, and how much, or what does it mean if I influence neighboring surfaces? And of course, are there any planned machining processes of the part afterwards, which brings me to residual stress and deformation and deflection? So therefore, starting with the discussion with the customer drives the whole simulation process afterwards, to have a clear goal and to know exactly where are my priorities. It downstreams through the whole optimization process, as well as the choosing of the right material, and of course in the end the right geometry.
Perfect. I think that's it on the questions front. So in that case, that wraps up today's presentation. Thank you everyone for joining us today. I hope you found the session valuable. If you do have any questions, anything comes to mind, or would like to explore any of the products mentioned today, please don't hesitate to reach out to your local representative. And thank you, Marcus, for your time.
Thank you very much.
Thank you all.